very great pleasure of me to introduce today's Charney lecturer. I first encountered Mike Wallace many years ago as a really bright graduate student down the hall from my office, and so I'm not terrifically surprised that he's progressed the way he's progressed after that. But Mike did his bachelor's studies at the Webb Institute of Naval Architecture. He told me that if he had done a little better in boiler design, he perhaps wouldn't have changed careers. And then he did his doctoral studies in meteorology at MIT. There, Mike and I were very fortunate to have a very illustrious faculty, and certainly Jewel Charney was the star, or a star, among this very illustrious faculty. And so when I invited Mike to give this Charney lecture, he said that he really felt particularly honored to deliver a talk named after Jewel Charney. He certainly made a great impression on all of us who came in contact with him. Mike's talk is titled "The Role of the Arctic Oscillation in Recent Climate Trends," but before I let him start, I think it's kind of interesting to reflect on how the subject, and when you listen to Mike's talk, how this subject picks up some of Charney's research and teaching themes. Certainly the paper of Charney and Drazen was pioneering in the subject of troposphere-stratosphere interactions. And those of us who took his course, who were lucky enough to take Jewel Charney's course, as Mike and I did, know that a great deal of that course was spent covering the subject of vortex adjustment, drawing on the early work of Arndt Eliasson. And I think you'll see some of that in Mike's talk. Well, it's certainly my honor to introduce this year's Charney lecturer and Revell medal winner, by the way, John Michael Wallace. It took me a long time to know his first name was John.
I'm nursing a cold here, so I'm going to try to keep my voice low. First, I wanted to say how honored I feel to have been selected to give this lecture, and I guess the fact that a person like myself who deals with observations would be selected to give a lecture honoring a man who is largely a theoretician says something about Jewel Charney also. Jewel was tremendously interested in phenomena, and he just really couldn't get enough of talking and speculating about what the nature of the different large-scale motion systems we observe in the atmosphere. One of my favorite memories of him was when he came out to visit us in Seattle, and we promised that we would go on a hike, and as usual, it was raining, and we donned our shorts and sweatshirts and went up a 6 or 7 mile hike up to a lake in the Cascades, and that was the day he wanted to sort out just what these teleconnections were and why we had these kinds of patterns. In some ways, I think the talk today is perhaps a continuation of that conversation, and we'll probably show you that we still don't have all the answers to questions like that. Well, I'd like to start this talk with sort of a historical perspective. And in this, I'm very much reminded of one of Harry Van Loon's favorite expressions. He always likes to remind me that there's nothing I've worked on that doesn't have long roots that go way back. And in that spirit, I wanted to go back to this phenomenon that we've been calling the Arctic Oscillation, and to relate it to this hypothetical elephant here, which has been known by several different names. And the first one, in terms of the history, if we to go back to the landmark paper of Walker and Bliss in 1931 or 1932, in which this was defined as one of three great climatic patterns. And in a paper that was I've read many times and could never quite figure out how he got these patterns, he ended up coming out with a set of correlations between an index of this North Atlantic Oscillation and a set of station data here: sea level pressure at these four stations, temperature at this list of stations in the months of December through February, which is the season that I'm going to be concerned with here, the Northern Hemisphere winter. And in effect, the time series data at these stations define the index of the North Atlantic Oscillation. He actually started in deriving this index with sort of a trial index in which he assigned a set of weights in a rather ad hoc way, and then he performed correlations with the individual stations, adjusted the weights, did more correlations, made more adjustments in the weights. And although it was a very informal way of analysis, what he did, it turns out, is very similar to one of the ways of doing empirical orthogonal function or eigenvector analysis. And in fact, his index is correlated with the leading principal component of these time series at a level of 0.99. It's virtually identical to the leading EOF of the normalized data for these stations. Just to show you where they are, on a map here, the map, the red squares are the temperature stations, the blue are the sea level pressure stations, and you see Iceland is included there, and Bermuda, and then I guess it's Vienna in Central Europe. So his resulting pattern, a poor copy of the figure that appeared in the Walker and Bliss paper, is at the top. And it's presented here. I'm just going to show the sea level pressure version of it. And so we see out of phase centers of action, so to speak, in the sea level pressure field over the temperate latitude Atlantic and the Iceland-Greenland region to the north. And this is the pattern that Walker and Bliss referred to as the North Atlantic Oscillation. This is a modern rendition of the pattern that was done by Todd Mitchell at University of Washington. And Mitchell, for this, took Walker's recipe here. He took his index and formed it each month on the basis of modern gridded data, but grid points corresponding to the stations in Walker's index. And since his data are global, he's able to make a global pattern, which is represented here. And you can see that over the North Atlantic sector, it's virtually perfect correspondence, totally independent data. So it just shows that Walker's pattern is reproducible. But the other thing you notice is that with the modern data, we see this pattern extending over a wider range of longitudes. Walker didn't see this because he didn't have data for these other areas. Then, just to get another perspective on it, here is the same pattern, Mitchell's version, repeated here, and then just remapped on a polar stereographic grid, exactly the same thing. And now you begin to get the idea of something that looks a little more zonally symmetric, involving a sort of a seesaw between the polar cap region and middle latitudes. So that's Walker's pattern. Now to come back to my original elephant slide, which is here. And let's look just briefly at another historical pattern, the zonal index cycle, which was very much a part of the MIT scene during the early years in the department. And it's interesting that the index cycle seems to me underwent something of a metamorphosis during the 1940s. When first mentioned in the paper of Rossby et al. In 1939, it was envisioned as a weakening and strengthening of the westerlies throughout the mid-latitude belt, just sort of fluctuations in the angular momentum of the general circulation. But as time went on, particularly as Mamias got involved in studies of the index cycle, it began to look more like an exchange of angular momentum between low and high latitudes. In this paper of Mamias in 1950, this is a couple of his figures, and I think that the bottom one is particularly telling here. Two contrasting pictures for different dates in the same winters. One in which the jet stream is in high latitudes, the other one when it's in low latitudes. And Lorenz in 1951, when he published a paper with empirical correlations of sea level pressure data, the model that he had in mind was very much like Mamias's. Interesting point of history at this time, Ed Lorenz referred in his paper to a bachelor's thesis by a man named Larry Gates, dated about the same time, investigating the connection between these two phenomena. Well, I'm beginning to believe, after many years of thinking of the zonal index cycle as largely a historical, interesting thing, but of no relevance, I'm beginning to believe in it. And I guess here is one piece of evidence that suggests that at least we shouldn't dismiss the idea. Here is a profile going from North Pole to the equator all the way to the South Pole of the variance of zonally averaged sea level pressure. This is based on, forget whether it's daily or monthly data. I don't think it really makes any difference. They look much the same. So remember here that the data are zonally averaged first, averaged around latitude circles, and then the variance is formed. And let's look first at the solid curve here, which is for year-round data. Not surprisingly, the variance is high in high latitudes and very small in the tropics. We know that's characteristic of sea level pressure, and especially when we zonally average, because the latitude circles are long in the tropics, they're very short. In fact, it scrunches down to a point at the pole. In fact, this doesn't even go quite to the pole. It goes to 70 degrees. But you notice that it's not a simple monotonic drop-off here. There's a bump, and that bump is accentuated in the cold season data, and the dashed line here is November through April, and there it's actually a secondary maximum, and you see a similar feature in the southern hemisphere. The lower panel here is the same thing, but this is for zonal wind, zonally averaged zonal wind, and you see prominent maxima here at 35 and 55 degrees. It's just what Mamias was claiming in his paper, and Lorenz mentions too as coming out of his empirical correlations with sea level pressure. Here is the leading EOF of that's empirical orthogonal function or eigenvector of the zonally averaged geopotential height field. And in this case, this is geopotential height not only at the surface, but all the way up into the lower stratosphere. And it's based on all months of the year. And instead of plotting geopotential height, what's actually plotted here is the zonal wind perturbations regressed on the expansion coefficient time series, or the principal component of that leading EOF. So this is regardless of whether you understand the statistical terminology, this is the leading mode of variability of the zonally averaged flow as determined statistically. This is what it looks like, and here again we have our maxima at 55 and 35 degrees latitude of opposing sign. And here is what the sea level pressure field looks like if we regress it on that same time series. And we see out of phase oscillation and sea level pressure between the polar cap and the mid-latitudes. So just to repeat that colored figure, I'm going to just like to go over here for the next couple of transparencies. I don't lose these. This is just a repeat of the color version of the sea level pressure signature of this zonally average. Well, we could call it the index cycle here, because that's in effect what it is. And now to go to the third thing, the thing that I've called the Arctic oscillation. I had censored that term in one of the previous versions. That's why it appears in black here. But this is the thing we've called the Arctic oscillation. This is the leading EOF of just the sea level pressure field by itself, the zonally varying sea level pressure field. It includes the data are not zonally averaged before the EOF is computed. This pattern has a long history in its own right. John Kutzbach, in a paper in 1970, was the first to show this, and it's been reproduced in papers over the years by Kevin Frenberth and by Dave Gutzler and I. And it's a very robust pattern. It's well separated from the subsequent EOFs, and it has this maximum over the high latitudes. Just to show you that these are rather similar. In fact, I think so similar that it'd be hard to say that they're not the same thing. Furthermore, here is, and this I should say is based on monthly data. Walker's index is based, to keep to historically true, is based on seasonal data. But here they are together, and it's almost a perfect fit. And then there are other indices of this pattern. Here's one that Jeff Rogers created. Actually, Björknes used it back in the 60s also. The difference in normalized sea level pressure between Iceland and the Azores or Portugal, Lisbon, Portugal, depending on the season. So this is based on just 2 stations. And yeah, I think this is all of them. So let me just put them all together, and you see there's not enough difference between them to really make it worthwhile discussing them individually. They're the same thing, and this is all in way of saying, that the zonal index cycle, the North Atlantic oscillation, and the thing that we've called the Arctic oscillation are all the same phenomenon. There's not room here for 2 different things. We shouldn't think of one as the local manifestation of the other. They're the same. So Jim used to get a little tangled up in things too, so I feel like this is not too bad so far. I've got to get right back to the right set here, which I'm afraid I may have left over here. Yeah. Okay, just one other little exercise with the EOFs. Now that we have the NCEP reanalyses, it's possible to do EOFs on global data. And when we do it on the global sea level pressure field, here are the two leading modes. And interestingly, the first one is not the one that I've been talking about. It's one that looks very much like it in the southern hemisphere. And the second one ends up being virtually identical to the one that we've been talking about. So the notion of this being a pair of modes in the respective hemispheres rather than one single pattern that's just in the northern hemisphere. So this raises the possibility that there's an important kind of pattern here that we might refer to as annular or ring-like modes in the two hemispheres. And in fact, the notion of such modes is not a new one. As we've seen, it goes back to Rossby. And it has a rich history in the literature to which Jules Charney made some very important contributions, and particularly the Charney and Drazen paper that Marv referred to. And these modes, we know, are characterized by interactions between the zonally averaged flow and the eddies. There may be stationary waves, it may be baroclinic waves, it could be either kind of eddy. And the zonal flow determines where the eddies are strongest, and it determines their structure. And the eddies, in turn, feed back on the zonal flow through the fluxes of heat and momentum. And they also drive a mean meridional circulation, the Ferrel cell in mid-latitudes, and the meridional overturning stratospheric circulation that feeds back on the zonal flow. And we have a rich history of the literature on these phenomena. And I've listed a few names here, but it goes on to include many of the people in this room documenting the interactions between the zonal flow, the eddies, and the mean meridional circulations in the stratosphere. There's a newer but very excellent set of literature on this for the southern hemisphere troposphere, involving people like Dennis Hartman and John Kidson, who have been analyzing what, in effect, is this mode here, and showing diagnostically how the eddies and the mean meridional circulation interact to produce those fluctuations. And there's also a rich history of this phenomenon in idealized models. A few of the names here. Some of these models are spherical, Earth-like models. Some, Panetta's work is with beta planes. But the notion that we have these very low-frequency modes that are essentially zonally symmetric and involve these kind of interactions. And there's a whole set of literature and diagnostic and theoretical tools that we can use for diagnosing these phenomena. And in fact, first half of Jules Charney's course was very much along these lines. Victor Starr's course here at MIT was exclusively devoted to this. And these are very powerful tools that enable us to make very strong inferences about how things work. Now, in contrast, I want to portray other modes other than zonally symmetric or annular modes, as sectoral modes that exist within one sector of the hemisphere, and they owe their existence to zonally varying heat and momentum sources. And there's also a rich literature on this that comes much later, though. It began more in the 70s. And a lot of observational work on zonally varying teleconnection patterns and theoretical ideas as well about how to diagnose those patterns. But the theoretical tools here in this three-dimensional context are more complicated, more difficult, much more difficult to use than the ones here. and the power of the inferences that can be drawn is also not as great. It's a lot harder to make progress in this path. So it's important how we think of these modes, whether we think of this as an annular mode on which we can apply this rich set of tools to diagnose, or whether we think of it as a zonally varying mode that I give up. So it's easy enough to divide these into types, but the real crux of the issue is how do we know whether a given pattern is one or the other? Well, one thing we can do is simply see how the variance is partitioned between the two, between the zonally symmetric flow and the eddies. And we've seen that in these modes, the zonally symmetric component of the flow does dominate. And that's not by any means proof that this is the essential nature of the mode, but certainly that is true. A second test that we can apply, sort of as a thought experiment at least, is to compare these modes to the kind of modes that would exist on a zonally symmetric planet. And in this respect, I think the comparison between northern and southern hemispheres, where we can think of the southern hemisphere as much more like a zonally symmetric planet, is in my mind very strong evidence that these modes should be thought of as annular. And just to illustrate that, here is the northern hemisphere mode, this time determined on the basis of EOF analysis of the sea level pressure field. This is what we call the Arctic, what Dave Thompson and I have referred to as the Arctic oscillation. We get the vertical structure here by regressing the zonally averaged zonal wind field upon the time series of this EOF. And here is the counterpart of that same pattern for the southern hemisphere. And we see in the sea level pressure field the same kind of structure, the same meridional scale, the same tendency for a seesaw between middle latitudes and high latitudes, the same latitudes here for the features in the zonal wind. To illustrate that more clearly, I can simply take these and turn it around so that we have the pole. Now, for both of them, the pole is on this side, the equator is on this side, and you see how cleanly they line up. So the meridional and vertical structure is very similar in the two hemispheres. The only difference here is the vertical extent into the troposphere, into the stratosphere. That's another matter that's largely irrelevant in the context of this discussion right now. So to come back to the sort of second test, this, in my mind, is a very strong reason for thinking of these modes as annular, and particularly for thinking of the northern hemisphere mode as not just the North Atlantic oscillation, but something much more generic than that, more fundamental than that. Now, the last thing that I want to spend actually a bit more time on is to discuss the temporal behavior as a way of identifying whether these modes are something more fundamental. And in particular, I want to suggest that these modes are notable in the sense that much of the trends that we've seen in the past 30 years project onto them very, very strongly. This is a point that was made by Ron Miller in his talk this morning. And to illustrate that, I just want to show a time series of I'll call it the Arctic Oscillation here. Actually, two time series. The lower one is based on the sea level pressure field. It's just the leading principal component of sea level pressure. And it's extended back into the past by taking the data, actually the time series out of Walker's paper that is published back to 1880. So we just took his numbers and normalized them for this blue curve. And you see how well they fit during the time that they overlap. And so that takes us back to here. We can go back even further if we make a proxy time series based on Phil Jones's surface air temperature data set. And to do that, we take, for the modern record, we take the principal component time series from sea level pressure. We correlate the surface air temperature field with it. We create a correlation pattern, and then we use that correlation pattern as a weighting function to go back further. It's very similar to what Alexei Kaplan and the group at Lamont has done for constructing ENSO back further in time. And you see how well these time series fit in the modern record and how it looks, how extraordinary this last 30 years looks in the context of that long record. So I would like to now show you some trend maps for the past 30 years. And we'll start with sea level pressure. The top panel is just the raw trend. In this case, in order to get everything to work together, we went from 68 to 95 to have a common period of record, so it's a little less than 30 years. This is the raw trend. This is the part of that trend that we could say is linearly congruent with the Arctic Oscillation, or the leading EOF of sea level pressure. And by linearly congruent, what I mean is that it is only that part that is coherent with the Arctic Oscillation on a month-to-month basis. If they weren't correlated, we'd get nothing here for this part. It isn't merely that they have a common trend. And you see how similar these are, and you see that what's left is the discrepancies, and what's left are mainly in the Pacific sector. Not surprisingly, that's where we have something else going on, ENSO. And in fact, if we want to go after that too, by the same kind of analysis, we can, by removing both, get down to a pattern that looks really bland. That's all that's left of the trend if we take out the parts that are linearly congruent with the Arctic Oscillation and with ENSO. Now I'm going to run through the same analysis for a set of other variables. I can do this fairly quickly. Surface air temperature. Here's the total. Here's the Arctic Oscillation part by itself. Here's the residual. You see there's quite a bit of warming going on in this is all January, February, March, even after we've taken it out, the Arctic Oscillation part. We can get a little more if we repeat that analysis, taking out ENSO as well. The total, the contribution from the Arctic Oscillation and ENSO together, and the residual, because it looks even a bit more bland, but there's still global warming, even in the absence of those signals in the surface air temperature data. Here's what we get, and here I'm just going to show you two. This is the total trend in zonal wind. And just want to be sure you can see how strong this is. This section extends from 20 degrees north to the North Pole. And you note the scale here. The trends in this 28-year, no, this is 30 years in this particular version. We have an increase in zonal wind of between 1 and 2 meters per second at the surface, but you see how it increases as we go up, and we've had changes in zonal wind in the past 30 years, 7 or 8 meters per second in the lower stratosphere at about 65 degrees latitude. So at the edge of the polar night, this essentially is an acceleration of the polar night jet during the winter months. This is the part of that trend that's linearly congruent with the Arctic Oscillation. And take my word for it, if you take this out, there isn't much left. All you get is just very light colors that don't, a pattern that doesn't look like anything interesting. In this case, taking out ENSO as well doesn't get you anything more because you've already got it all with the Arctic Oscillation. Here's the counterpart with temperature. Now we're getting, each one of these looks more and more like the IPCC documents. And these are the total trends, and we're having downward trends in temperature in excess of 5 degrees C over the polar cap region, and about 3 or 4 degrees of that is coming from the part that's linearly congruent with the Arctic Oscillation. This one isn't as good, but I know there are a lot of people in this room interested in ozone. And so these are the trends in ozone expressed in Dobson units. Decreases on average are on the order of maybe 20 or 30 Dobson units over the polar cap region, polar to 40 degrees. But there are decreases as much as 60 or 70 Dobson units over this region, and less over this region here. And here is the part that's linearly congruent with the Arctic Oscillation. Notice how we pick up a lot of the pattern in the total trends comes out in here. So that when you take this away, you've lost much of the structure in it, but you've accounted for only about half the decrease. So roughly the other half of the decrease is sort of amorphous, and it just represents an overall decline in ozone over the polar cap region. Now, to give a little more of an overview of these trends, here's a figure that Dave Thompson prepared for just a selection of variables in different regions. Eurasian surface air temperature, this is a big rectangle covering much of the Eurasian continent. The total trend over this region in the months of January, February, March in surface air temperature is 3 degrees in the past 30 years. That's enormous compared to the global average trend. Of that, about half is linearly congruent with the Arctic Oscillation. I think we can reasonably ascribe to dynamical causes. The remainder is not. Sea level pressure over the polar cap region, fall of almost 6 millibars, enormous change for 30 years, of which almost all of that is due to the Arctic Oscillation. There are rainfall patterns with this as well. They look very much like what has been documented in connection with the North Atlantic Oscillation. And over northern Europe, extreme northern Europe, it's been getting wetter. Norway has had a phenomenal amount of rain, Scotland as well. Norwegian glaciers are growing now because of the mass balance. Despite the warming, it has snowed. It snows so much in recent winters that they've been seeing an increase. Most of that is linearly congruent with the Arctic Oscillation. Then southern Europe, we have the opposite, and really substantial changes in rainfall in Spain, Italy, across the Balkan countries, Greece, across into Turkey, with most of that linearly congruent with the Arctic Oscillation. Total column ozone, we've had averaged over the region polar to 40 degrees, we've had a loss of about 50 Dobson units in the past 15 years. It's quite a substantial loss, something like 15% or so, of which about half is linearly congruent with the Arctic oscillation, and also very big changes in temperature, and cooling, and substantial contributions there. Finally, just one last picture on this, just a long perspective. The Arctic oscillation time series repeated again here in the middle panel. This is the surface-based Arosa ozone record going back to the 1930s. And I should say this is inverted. So up means down. I mean, this means ozone decreases here. And this is Eurasian surface air temperature. Just, in this case, just over that rectangle over Eurasia. And you see the nice correspondence and correlation coefficients between these time series based on monthly data up in the 0.8 range. So this is all in way of saying that there are some interesting aspects of the temporal behavior of these modes that are suggestive that there's something going on that transcends the kinds of things that we see in most of the sort of dynamically based teleconnection patterns. Now, on the high frequency end, on the week-to-week end, there's some interesting things too. This is a slide from a paper that is in, I believe it's in press for JGR by Mark Baldwin and Tim Dunkerton, and it gives us a long view of a time height section of geopotential height over the polar cap region. So the section goes, you see at each one of these panels, it goes from the ground up through the lower stratosphere here. And we start back in the 50s, and we work our way through up to the present in the lowest panel. And you see that there are kind of alternating splashes of color and then sort of blank areas. Well, the splashes of color are occurring in the wintertime, January, February, March. This is northern hemisphere, polar cap. The white blank areas are the warm months of the year. So we're seeing, and the reds and blues are essentially showing us temperature fluctuations over the as reflected in the geopotential height field over the polar cap. And the reds represent warmings, and most of the reds are associated, the warm colors are associated with stratospheric warmings. One thing you notice is that there's lots of stratospheric warmings in the upper panels, relatively few in the lower panels. Stratospheric warmings are getting less frequent. The other thing that's interesting is that there is a tendency, for most of these, to have some downward propagation. And that's indicating that these temperature changes and geopotential height changes are occurring first in the stratosphere, and then they're showing up shortly afterwards in the troposphere. So then we come to the question of what, if these annular modes are of interest, why should we have annular modes in the first place? And I have a few thoughts here as to some reasons why we might observe such a phenomenon. First of all, annular modes, since the contours in the annular modes line up with the contours of the background flow, which is mostly westerly, as in this lower figure, we have a situation much like this, where the orange contours represent, say, the geopotential height anomalies, and the blue represents, say, maybe the 500 millibar or jet stream level flow. Everything lining up. In a pattern like this, we don't have very strong advections of temperature, vorticity, potential vorticity. Modes like this are not very strongly damped. In contrast, sectoral patterns, we have situations much like this, where we will have strong advection terms in the balances for these terms, and to maintain anomalies that look like the ones in that upper panel, we have to have strong local sources of heat and or vorticity to maintain them against those advections. Much the same situation with blocking, where blocking configurations manage to get themselves lined up with the zonal flow, so there's relatively little advection going on. So it may be that annular modes are favored simply because they are weakly damped. Another intriguing idea is some experiments of Derek Williams back about 20 years ago that suggested that the Earth as a planet is in a sort of a regime where it's undecided as to whether it wants to have a single jet stream at around 30 or 35 degrees latitude, or two jet streams, one at say 30 and one at 60. And in his experiments, if you increase the rotation rate of the Earth, you would go towards that two-jet regime. And so perhaps we're in that situation where the high index of this mode, where we have the strong high latitude jet, is like going to a two-jet regime. Well, in a little bit lighter mode here, just to end up in way of a summary, I'd like to try to sort of dramatize the differences between what I've called the annular modes and the sectoral modes. Seem to have gotten everything somewhere here. I have a few more. Can't lose this. This is the best part. So it comes down, I guess this issue of how we think of these things comes back to names. And I want to question the name North Atlantic Oscillation here. And to do that, I would like to sort of summarize by sort of looking at just summarizing the properties of the North Atlantic Oscillation as we have usually thought of it, versus this paradigm of annular modes that for the name I'll use the term Arctic Oscillation. And I'd like to do that side by side with sort of a whimsical analogy. And so to work our way down the page, the image, and this is the way we think of it. The North Atlantic Oscillation certainly conjures up the image of a dipole pattern in the North Atlantic. The annular mode conjures up quite a different image here, just as we have different images of this person. The domains are certainly different. The North Atlantic Oscillation lives in one domain, the North Atlantic, only in one hemisphere. The annular mode lives in two hemispheres. It's just as prominent in the southern hemisphere as in the northern hemisphere. And we think of it as a hemispheric phenomenon. Well, we think of Superman here as occupying the whole Earth. He gets around, and he's been around on other planets as well, like the southern hemisphere. Species. We think of them as having fundamentally different kinds of behavior that can be diagnosed by different tools, and likewise we think of quite different species here on this side. Probably the most important thing in this list that I want to spend just a little bit longer on is the things that sort of drive Superman and drive the annular mode here. If we think narrowly in the context of the North Atlantic Oscillation, we're going to be drawn to rather local phenomena like the interactions between the North Atlantic Oscillation and sea surface temperature over the Atlantic sector. That's a good problem to study in that context. that's a good problem in any case, and it's on the list over here too. But I'd like to suggest that there are lots of other things that the annular modes can respond to. And Ron Miller this morning gave a very stimulating talk about how global warming could conceivably cause a drift in the annular modes. Similar possibilities for ozone. It's also been suggested by Alan Robach and others that volcanic eruptions have a signature in the annular, well, they've called it the North Atlantic Oscillation, but I prefer to think of it in this context. In a similar way, Superman here, of course, is responsive to his editor and to Lois Lane. Superman has a soft spot in his heart for Lois Lane, too, but he has a much broader agenda here in the things he's interested in. With speed here, this was just kind of an attempt to get across the idea that the Arctic oscillation is discernible even in daily and weekly data, and it may be of interest in terms of long-range forecasting and how stratospheric warmings interact with phenomena at the Earth's surface. In contrast with the North Atlantic Oscillation, we have to think in terms of long time scales like a season. We can't even see it if we look at very short time scales. So with that as background, my final slide here, I'd like to suggest that we've seen, by seeing that all these phenomena are the same, it's like having witnessed this transformation here. And I was going to also dramatize, since I've got, I was in Charleston the other day. Whoops. I can't quite. So, if you had witnessed that kind of transformation, what would you say about it? Would you say that Clark Kent is really Superman, or would you say that Superman is really Clark Kent? And I'm suggesting that if you really think this way, then we should think that the thing we've been calling the North Atlantic Oscillation really is something more. Thank you.